Hello, I'm Norbert Schörkofer, and I would like to propose a terrestrial field experiment to investigate what we call subsurface-atmosphere vapor exchange theory for Mars. So I will briefly, explain that theory and what it explains on Mars, and open questions of what we observe on Mars, but isn't explained by the theory. And then toward the end, propose a field experiment specifically designed to investigate these vapor exchange processes in the soil between an ice table and the atmosphere. Now, here are two images and parameters for Mars and the dry valleys of Antarctica. The dry valleys of Antarctica are the driest desert on Earth, and driest in terms of absolute humidity, not in terms of relative humidity, but in terms of absolute humidity. So they are, the annual mean vapor pressure, water vapor pressure there in the upper, or in this particular location in Beacon Valley, Antarctica, is about 10 times lower than the triple point pressure of H2O, which is the minimum pressure for the liquid phase. Under current conditions. But on Mars, the vapor pressure is in a range of microbars. So Mars is still far, far drier in terms of absolute humidity than even the dry valleys of Antarctica, and therefore very far from the liquid phase. And what this implies is that any mass exchange of H2O within a buried ice table, an underground ice table, and the atmosphere is by vapor diffusion, not by percolating liquid water. And it's a situation which is actually quite rare on Earth. And here are, two diagrams which just outline the climate conditions or annual mean conditions. So to the right is the phase diagram of H2O and Earth, depending on what latitude one is. These are annual mean conditions or approximate annual mean conditions. We can have melting and freezing, but we also can have sublimation and desublimation in some parts, like the dry valleys of Antarctica. But on Mars, we only have sublimation and desublimation, at least on annual mean conditions. And if you have a buried ice table, these temperatures are characterized roughly by the annual mean conditions. Now, let me also point out, if you add salt, and Mars has lots of salts, then it moves the liquid-solid boundary, but does not move the solid-vapor boundary, right? Because you have solid ice and you have solid salt crystals and a mechanical mixture, so each has their own phase diagram. So none of what I say, or almost none of what I say, changes in the presence of salts. Still, the vapor exchange theory remains valid. Now here's then, the most direct observations of a near surface ice table on Mars by the Phoenix lander, which landed at 68 latitude. And it unintentionally, the rockets as it landed blew away about 5 centimeters of material and exposed an ice table. And this ice table is perennial. And the theory is that there is vapor, diffusing from the ice table atmosphere, but there's also, importantly, vapor diffusing from the atmosphere into the ground. So H2O is only a trace gas in the Martian atmosphere, but it's an important trace gas. It controls the extent and the depth of this ice. And the surface is ice-free. So in winter, there's lots of CO2 ice, but only minimal amounts of H2O ice. But even so, there's enough humidity, enough vapor in the atmosphere to balance the vapor pressure of the ice. And so the physical system we are dealing here is illustrated here. So we have an ice table, then we have a soil or regolith layer, and vapor goes not only out, it also goes in. And then there are temperature variations, and they can be huge. So Mars, the daily temperature max-min difference is easily 100 Kelvin. So we have to understand vapor diffusion in the presence of these large temperature amplitudes. And while the water diffuses out or in, It can, sublimate or desublimate. It can be adsorbed and desorbed. So there's all these microphysical processes which can go on, but the transport is ultimately due to vapor diffusion. And so here are equations for vapor diffusion in non-isothermal environments, and there are various terms. And this paper by Hudson et al. In 2007 contains a detailed listing and derivation of all these terms. And one quickly finds that under Mars conditions, that the most important term is just the gradient in the vapor density. So it's a gradient in the absolute humidity, not in relative humidity. So the gradient of absolute and relative humidity only point in the same direction in an isothermal environment. But if it's a non-isothermal environment, these can be different directions, sometimes even in opposite direction. So it's the absolute humidity really that matters here. And so I find it insightful to think of a stability of ice, as we call it, or any fine kind of vapor diffusion in terms of the absolute humidity, kilograms per cubic meter, number of molecules per cubic meter, and it's almost proportional to the partial pressure by the ideal gas law. These are the quantities which dominate the direction and absolute amount of vapor flux in a sublimation environment. Well, any environment, but it's a dominant form of vapor diffusion, is a dominant form of H2O mass transport in a sublimation environment. Now here, to be even more detailed about it, is a microphysical calculation of vapor transport. And the red are temperatures, and there's an ice table at 20 centimeter depth. So that's why there's a change in gradient. And here is the blue lines are partial pressures, and then there is periodic sublimation and desublimation going on here. But if one averages these pressure or vapor density over a long time, or here 1 Mars year, one ends up with just a linear dependence, and the net flux, the time averaged flux, is just given as a difference between the vapor density at the ice table and the annual mean vapor density atmosphere. It boils down to this very simple, the boundary conditions derive the vapor flux in the long term. And so here, this equation here says the stability of near surface ice is given by these difference in annual mean. And then Marshall mean latitudes, these values, or that threshold value, is about a density of 1 milligram per cubic meter, or something like 0.1 to 0.2 Pascal, which is a frost point temperature about 200 Kelvin, which is a latitude of about 50 degree on each hemisphere. And indeed, water ice, near surface water ice, is present for both of these latitudes. And the next slide actually shows this, based on neutron spectroscopy for Mars orbit. There are many technical details here which are described in a paper by Dietz et al. But at least, there clearly is a relation between the prediction of vapor equilibrium between the atmosphere and the ice table and what's actually observed. Right? And also, there's no other theory, there's no competing theory other than vapor exchange equilibrium, which even would remotely be able to describe the depth and extent of near surface ice on Mars. So it's the only viable sort of theory to begin with. Now, but there are many aspects. So this theory has never been really verified in a terrestrial setting. There have been some lab experiments, have been observations on Mars, but it's never been really scrutinized in a field experiment. And here are some of the unknowns. So first of all, near surface ice is found on Mars equatorward of equilibrium latitude. So there are impacts which expose ice. But that ice is a greater depth than a meter or so. So we don't know if it's just a delayed response, or is there are some deviations in the vapor exchange theory which need to be understood. And here is a list of possible explanations or uncertainties. And rather than the readers all, let me just point out some which could be explored with a field experiment, terrestrial field experiment. One is, how do you even know what the annual mean near surface humidity is, right? We have to infer it from orbital observation and so on. But there's all kinds of physical processes which could happen. So for example, in the morning, there's going to be desorption of water from the soil to the atmosphere. In the evening, it's going to be absorbed again. So if the mixing heights in the morning, evening are different, it may affect the time average of the humidity. That's a process which has not been quantified yet. Or, for example, point number 4 here, the air temperature and the ground temperature are often different, especially in the tenuous Martian atmosphere, and there are offsets which need to be, or could be offsets which need to be better understood. And then there is point number 7 here, unknown unknowns, right? It's possible that there are important processes going on, which are not even on this list. And we really have to identify or exclude all these various processes. And, number 7 is perhaps the most exciting prospect of a field experiment. And as unexplored as these process of theories is at this stage, it's quite possible that there are other important processes going on which you're not yet taking into account. So here is the proposed field experiment. So first, it has to be in a sublimation-dominated environment. That doesn't exclude that the temperature goes above 0 Celsius, but if the temperature does go above 0 Celsius, no ice or water must be present. So, or if it is present, it has to be its influence has to be quantified. And there are few places on Earth where this will be the case. So the upper dry valleys of Antarctica is one such location. And of course, the reason why it's so rare on Earth is, ultimately why this wave exchange theory hasn't been worked out in greater detail yet, because on Earth, it's hard to find a place where it's actually the dominant process. And so the goal is to measure absolute humidities above the ground and beneath the ground, right? So the humidity, vapor diffuses through the pore spaces in the ground, and therefore we want to measure the humidity in the pore spaces of the ground. And the theoretical prediction or expectation is the following: that the long-term average of the vapor absolute vapor density, or the vapor density near the surface and beneath the surface are the same, because vapor diffusion has to equilibrate them. That's a fundamental prediction. And then if the ice table is retreating, then there should be a sort of a steady increase, a roughly linear increase of the time averaged vapor density with depth towards the ice table. So these are the two predictions waiting to be validated or in field experiments, and especially quantitatively, there's a lot of uncertainties to be assessed in a field or in this environment in general. And here there's text of what I already said, the expectations of a field experiment, so I can jump to the conclusions. So atmosphere subsurface vapor exchange controls the distribution of near surface ice on Mars, at least in a top meter or so. There are a series of papers which have shown that, but it's a situation which is unusual or very rare on Earth. And a field experiment in a sublimation dominant environment could help a great deal in validating this or challenging this, but in any case to quantitatively improve our understanding of these processes. And the last point here, I haven't really talked about it, but if I'm asked, what's an important measurement for Mars, it would be the near surface humidity at a place which has ground ice. That would help us a great deal to quantify the extent and depth and extent of ice on Mars.